Alright, so we're going to start with removable discontinuities. I'm going to show you what those are and why they're called removable, and then I'll show you the difference between a removable and a non-removable discontinuity. Okay, so what I've got here is a rational function, top heavy, and what I want to do is show you that this actually has a discontinuity when the bottom is equal to 0 that can be removed. So if we factor this numerator in x plus 3 times x minus 3 over x minus 3, you might think that there's a vertical asymptote at x equals 3 because that's what we saw yesterday. But I also mentioned in the video yesterday that if you get the denominator is equal to 0, you have to make sure that it doesn't also make the top 0. So when x equals 3, it makes the bottom 0, but also if you plug in 3 in the numerator, you also get 0, and you get something that's indeterminate. You'll learn that word more later on in pre-cal and also in calculus. This does not necessarily mean a vertical asymptote. So what we're going to do is we're going to cancel these common factors. X minus 3 and x minus 3 cancel, and that means that it was not a vertical asymptote, it was just simply a hole. And what we're left with is y equals x plus 3. We've actually divided these and it worked out evenly. That means that the remainder graph, this graph that I'm getting ready to move around, the remainder graph just looks like x plus 3. So let's go grab a hold of that and do an x plus 3. That's a y-intercept of 3. Of course, we know the y-intercept is 3 because we replaced the x with zeros and we would get 3. And at that point, once we've canceled, there is now we're going to put this little hole where it should be. Now, where are we going to put this hole? We know it's at x equals 3. It's at x equals 3 because that's the factor that I canceled. But what's the y value? Where does this hole go? The way you find the y value is you're going to plug 3 in for x into the remaining. So what I have left over is we're going to plug in 3 for x, and you're going to get y equals 6. So this means this little hole needs to go at 3, 6. So if you get 0 over 0, and there's a number that makes the bottom 0 and the top 0, that is not a vertical asymptote. It's simply a little hole in the graph. And this is why it's called removable. We can remove it by doing the little factoring. X plus 3 times x minus 3 over x minus 3. This is removing it. Boom, we removed it. It's gone. And what we're left with is what the graph looks like everywhere else except at 3. So that's called a removable discontinuity. It will happen if you get 0 over 0. Now we still have to say for our domain that x cannot equal 3 because that's still a discontinuity. Okay, so let's take a look at the difference between removable and non-removable. Alright, what you have in this first graph is an asymptote at 0. And this is like our parent function. One over x, right? Which has an asymptote at x equals 0. So its parent function is 1 over x. And this cannot be removed. There's no way to remove that asymptote. You can't cancel anything out. This is just 1 over x. And what happens is when x equals 0, we have an asymptote, and there's not a common factor on the top and bottom. So that one is non-removable. This one on this side, this little hole, that's all that is. It's a if I try to drag this over as an answer, that's just a hole. That means that there was a common factor. That's not a non-removable discontinuity. This one is non-removable. And it's non-removable when x equals 0 because we did not get a common factor on the top and bottom. Alright, so let's keep going here. Now I want to practice a little bit more with what we're doing yesterday. Let's identify our horizontal and vertical asymptotes. So horizontal asymptotes, remember we have 3 rules. top heavy, bottom heavy, or equal. These are even or equal because they're both x to the first, so our horizontal asymptote is going to be at y equals the ratio of those coefficients. So that's going to be at y equals 1/2. I'm going to pull the graph out here in just a second. Our vertical asymptote is going to be when the bottom equals 0, and that's at, we've set 4x minus 1 equal to 0 at 1/4. And we also have to make sure that doesn't make the top 0 because it might have been a hole, but it doesn't. If you plug in 1/4 for x, it doesn't. So we know that our domain is x cannot equal 1/4. Now what about the zeros? What we're going to do is to find our x-intercepts is we're going to set the top equal to 0, and that happens when x equals -1, so we should have a 0 at -1. And the y-intercept is we replace 0 for x. So our y-intercept is going to be 2 times 0 plus 2 over 4 times 0 minus 1, and we get -2. So we should have a graph that touches here at -2 and a graph that touches here at -1. We should have a vertical asymptote at 1/4. I'm going to show you in just a second. And also a horizontal asymptote at y equals 1/2. But something that we're going to practice in a little bit is how do I know what that graph looks like over here? On this side, is the graph in quadrant 1 or is it down here in quadrant 4? So one thing we can do is we can do some test values. Let's find f of 2. Let's figure out where the graph is at 2. If I plug in 2 for x, I'm going to get 2 times 2 plus 2 over 4 times 2 minus 1. And I get 6 over 7. So I know the graph is above the x-axis. It's up here. So that helps me know where the little branch goes. So let's see. We got our x-intercept, y-intercept, our asymptote, a horizontal asymptote at 1/2, vertical asymptote out here at 1/4, and let's see what that looks like. Did we get it right? Pull it out here, something like that. There's our vertical asymptote. Notice the graph will never touch that. Here's a horizontal asymptote at 1/2. We've got our intercepts right, and we knew the graph was above that line. All right, let's keep practicing a little bit longer. All right, so let's say everything we know about this graph of 2x plus 5 over x minus 1. The first thing I want to do is I want to find some asymptotes. Vertical asymptote happens when the bottom equals 0. And that happens at x equals 1. To make sure it's not a removable discontinuity, we're going to plug 1 into the top. And you'll see if we plug 1 into the top, we get 7. So that's a vertical asymptote. And if we look at the next page, that's what I have graphed here. I've got a vertical asymptote. That's almost always what I do first. The next thing I want to do is look at a horizontal asymptote. Horizontal asymptote, you know, we've got those 3 rules. Is it top heavy, bottom heavy, or even? This one is even because it's both x to the first, so we look at the ratio of the coefficients. And that horizontal asymptote is going to be at y equals 2. And that's typically the next thing that I graph. And you'll see here, I've got that graphed at y equals 2. Now, do we have any kind of zeros? What about x-intercept? We set the top equal to 0. And we get x equals -5/2, so that's the point -5/2, comma 0. And what about the y-intercept? The y-intercept, we replace 0 for x, and we get what is this going to be? -5. So that's the next thing I do is find intercepts. So let's go take a look at that picture. So there's our intercepts. And now from there, you might ask yourself, how do I graph this? This side down here in mostly quadrant 3 is pretty easy to see. This graph must look like this on this side. But what about over here? How do I know is the graph up in quadrant 1? Is it down here in quadrant 4? Is it over here in quadrant 2? What goes on? So that's where you might have to check some values. And that's this next page. I've checked way more than you need to. But here is a whole bunch of values for x. And you can look at their y values. You plug them in, and you can figure out where those dots are. And so on this next page, I have those, and I've plotted way more than you need. You really only need one to figure out where it's going. And so now that you have some extra dots, you can fill it in. Let's write out here what we know also. What's the domain here? The domain is x cannot equal, way back here when we were doing our vertical asymptote, x cannot equal 1. So every single number except 1. Alright, so let's take a look at one last thing that has a hole in it. X squared minus 4 over x minus 2 times x plus 3. Let's take a look at that one. And this is a new example. And I would factor the numerator in the x minus 2 times x plus 2, and the denominator is x minus 2 times x plus 3. So let's answer a couple questions here. What are the vertical asymptotes? Well, the vertical asymptotes, you set the bottom equal to 0, but you better make sure neither one of those values also make the top equal to 0. When I set the bottom equal to 0, I get x equals 2 and x equals negative 3. However, my vertical asymptote is only x equals negative 3. Because this x minus 2 also appears in the numerator. That is a removable discontinuity, which means that there's a hole in the graph. So I know there's a RD, or a removable discontinuity, when x equals 2, and the way you get the y value is you plug 2 into the remaining. The remaining function is x plus 2 over x plus 3, so that's 4 over 5. So that is a hole. Horizontal asymptote here would be, I'd have an x squared over an x squared, because if you multiply x minus 2 times x plus 3, you're going to get x squared plus x minus 6, so I'd have an even one, and that would be at y equals 1. We would have a domain of x cannot equal 2 and x cannot equal negative 3. Even if it's a hole or a vertical asymptote, we still remove those from our domain. And then we'd go through and do our test points and all that other stuff. So we'll practice this tomorrow, and we're going to be doing a worksheet on this that I'm going to have you guys turn in. So I will see you guys then.